the domain, it's a descriptor of the function as well, right? So we are going to talk about this topological descriptor read graph in a little bit more detail. To recollect, we had used this simple example of a height function defined on a torus, and we said that the read graph is defined by taking the quotient of the domain with the equivalence, using the equivalence operator. So the equivalence operator will take it considers 2 points as being equivalent if they belong to the same connected component of a level set. So, this quotient space is what you get on the right. It is called the read graph, right? If you don't want to think along the lines of quotient space, I described a simpler way to understand the read graph, which is the following. You take every level set of your function f, you pick every connected component, you shrink it to a point, or you map it to a point. The image of this mapping is the read graph, right? What you see on the right. So the read graph, we saw the definition as the collection of, as the quotient space of this domain under this equivalence relation. We talked about how the read graph is the image of this map, right? The map that takes every connected component of the level set and maps it to one point. That's the read graph. Now, it is a topological structure. Like I said, it is a descriptor both of the domain and the scalar function. It represents the level set topology in a nice abstract way, essentially from the video. But why do we care? Why do we want to study this? This abstract representation allows us to study patterns in our data. It allows us to produce a feature-directed visualization of the data. Right? It allows us to display an overview of all features in the data. It is simple. Its method is very simple, but it turns out to be quite powerful, and it has a lot of nice probable properties. Right? In terms of applications, we will see later in the lecture that it has a wide variety of applications, both in terms of domains, application domains, and in terms of the different tasks that it supports. Moving towards an understanding of the properties of the read graph and how it can be applied towards data and shape analysis, let's go back to its definition. Right? Nodes in the read graph clearly correspond to critical points. We saw that a few times. Right? You already saw that relationship. What do the arcs represent? Right? We saw already that an arc is a collection of points that come from a mapping of these level sets, right? So here is a more kind of involved example with multiple merges and splits and the corresponding read graph on the right. Every arc in the read graph corresponds to a collection of, so let me play that video again. It represents a collection of level sets. The colors match, the colors of the level set components and the arcs match. So essentially, every arc in the read graph is a map from a collection of level sets. So if you take this collection of level sets, they form a cylinder, right? And that cylinder looks like this. So every cylinder on the left is essentially mapped to one arc on of the read graph. So thinking about it in the other direction, you can interpret every arc in the graph as a, a cylinder in the domain. The cylinder is a nice feature in the domain because it's a collection of level sets who all of whom have similar topology or exactly the same topology in terms of number of connected components, right? You can deform one into the other. So you can take any example on the left to understand this. You pick, for example, any level set in the red cylinder. Each one can be deformed into the other, right? So this is a nice abstraction. So selecting arcs in the Reed graph allows you to select features of interest in the domain. Okay. So each arc corresponds to one cylinder, right? So that's a nice mapping. The endpoints of the arc are critical points, right? So with that in mind, let's talk about some properties. The degree of the nodes is the first thing we want to study, right? So the Reed graph is a graph like any other graph, but it's a special graph in the sense that the nodes can either have degree 1 or degree 3. Now, why is that? The extrema, which is maxima and minima, have degree 1. These are the leaves of the graph. You can immediately see why the degree has to be 1, right? Because the number of connected components went from 0 to 1. So these are essentially leaves of the graph. All the other critical points that map to nodes represent a merge or a split event. So either two components merge to one or one component split into two. So hence the other nodes in the graph will have degree 3. So this makes the Reed graph a special graph, right? Of course, bounded degree, but more specially, the degree can either be this 3 or 1. We use this property to prove some nice bounds on the size of the graph and so on. Often in practice, the Reed graph is augmented by inserting additional degree 2 nodes. So these degree 2 nodes are the regular points, right? They are introduced often if you want to store the geometry, right? But this is an option. It's not always done. So an augmented Reed graph will have nodes of degree 1, 2, and 3. Right? Okay. So with that in mind, let's talk about the components, right? I referred to this earlier as well in response to a question. The terminology here, Betty sub 0 or beta sub 0, right? I won't formally introduce it, but this beta sub 0 refers to another topological descriptor which captures number of connected components. Beta sub 1 captures another topological feature called the number of tunnels, right? So every connected component from the Reed graph corresponds to a connected component of the domain. So remember, now we are not talking about connected components of level sets. We are talking about connected components of the entire graph, right? So the number of connected components of the graph is exactly equal to the number of components of the domain of your function, right? So if M is the domain of your function. The number of cycles in the Reed graph R, which is written as Betty sub 1 or beta sub 1, is upper bounded by the number of tunnels in the domain. So the number of tunnels beta sub 1 is a very useful topological structure that is often studied in topology, right? This is called the Betty number with index 1. So what we say here is, no matter what function you choose on the domain F, its Reeb graph, right? If you look at its Reeb graph and you look at the cycles in that Reeb graph, it is upper bounded by the number of tunnels in the domain. So in the case of the torus, the number of tunnels is 2. So the number of cycles can never be more than 2. The number of cycles in any Reeb graph that you have can never be more than 2. Okay. So this is very important for us, because if you look at the corner case where your domain has no tunnels, right? If your domain has no tunnels, for example, a domain such as a sphere, right, has no tunnels. There is no tunnels, the English word tunnels, right? Has no tunnels, which means that the corresponding graph should have no cycles, 0 cycles, which means it should be a tree, right? So this special case is very important, because people study this special instance of the Reeb graph when it is a tree. Okay. So a couple of structural properties.
Sorry, one quick question, Vijay.
Please.
So from maybe the other case may be interesting to you. Like, is there any condition that there is equality here for the beta one?
Yeah. Right. So I don't know if I have it in the slide. So in a paper, it's about 15 years old now, we proved the equality, right, for the specific instance when M is a 2-dimensional manifold. Not equality here, but there is a beta 1 over 2, a factor of half. Right? We showed equality only for the case of 2 dimensions. In the case of higher dimensions, we showed both lower and upper bounds, and showed instances where both lower and upper bounds could be reached. Right?
Okay, so, okay, I will take a look at that.
Yeah, so there is a paper. I think I have it in one of the reference at the end. The name of the title of the paper is Loops and Reeb Graphs.
Okay, yeah, sure. Thanks.
Right. So I don't know if okay, I think I have a part of the answer in the slide. So the number of, so I'm not going to talk about this in great detail though, because it involves some, it's a simple proof, but it involves some introducing new terminology. So for a simple surface, which is closed, no boundaries and so on, if the number of loops that you count in the Reeb graph, right, this is exactly equal to the genus, right? So that's the equality that I was talking about. The paper talks about the general equality condition, right? So this is just, again, I'm using plain English here. So the genus of the surface tells you the number of loops in the Reeb graph for surfaces. If you have surfaces which have boundary, right, then the genus is a lower bound on the number of loops in your Reeb graph. The upper bound is given by the genus together with the number of boundary components, which is H. Okay. And there is a similar such condition in higher dimensions as well, and for non-manifolds. So simply connected domains are those domains which are essentially a sphere, no tunnels, right? In those cases, the number of loops is 0, right? So this is I actually wanted to essentially derive this particular expression, which is the reason I introduced the notion of loops and so on. Contour trees is the name given to a loop-free Reeb graph, right? And this is a very special instance and a very popular instance. And the reason being that often your data is the scalar field is defined over a volume, right? A cube volume, which is simply connected. There are no holes or tunnels inside that domain. So often in practice, we deal with contour trees for scientific visualization problems. if you are looking at modeling problems, shape analysis problems, the Reeb graph plays a more important role, right? Because often the surfaces are non-simply connected. They have tunnels and loops and so on. Okay. So I want to quickly give you a picture of the contour tree, because when you don't have cycles, there are some nice properties that kind of really jump out at you. So I want to show one such property, right? So one reason for introducing this property is that in many problems in shape analysis, you want a good representation of your shape. And the result that I'm going to show actually has some analogous it has some counterparts in shape analysis. Okay, so so the contour tree, the definition is still the same as the Reeb graph, so you can just follow that. But let's look at the setting more from the viewpoint of contour tree. So the domain is simply connected in 2D, which means that the domain is just R2, for example. So just the plane. And here I'm showing what I show is the function using a grayscale map. So lower values are mapped to darker gray, and higher values are mapped to white and lighter gray. Okay. You can see that there are two minima, at least B and C. Well, there's a third minimum, A, right? And what you see on the bottom is the Reeb graph, or the contour tree in this case. So no cycles, right? So there are three minima, and there are a bunch of saddles. Each saddle you can immediately see has degree 3, and the reds are the maxima, right? In your mind, you can, let's say, we think about how the critical point D, right, the saddle D, represents the merge event of contours that were formed from A and from B, right? So there were contours formed from A and B. These contours grew, and then they merged at D, right, and formed a single component, right? So here is a kind of a picture in with an animation. There are two minima. The two contours are shown. That's the boundary of the black region. That's the contour. It keeps growing. At some point of time, it splits here because it reaches the boundary of the domain, right? And one component terminated here at the maximum, and another terminated on the left at the maximum. And then you see that the components are now shrinking towards the maxima. They again split at the saddle. The one on the left will now die, and then the one on the right will die, or the other way around. The one on the right probably dies first. The one on the left died first, and then the one on the right. Okay. So this evolution is again captured in the form of a tree now, because there are no cycles. Right? What is crucial here is that this tree structure maps to these cylinders. We saw that, right? But before we apply this mapping, it's important to be able to handle noise in our data, right? Why is that important? So let's take this simple example to understand why. Right? So here I have a very simple terrain on the left, right? So the scalar function is just the altitude, right? And there are two maxima at 80 and 90. The saddle is at 50. Right? You can imagine that the maximum at 80 is really, really small. It's shown as 80, but let's assume it's at let's say 60 or 55, right? So essentially, what we have is a big mountain with a peak at 90, whose slope happens to have a very small bump, right? Very small bump on the slope. Now, this small bump is essentially noise, right? And I would like to remove that noise before analyzing the function. How do I recognize that this is noise? A, how do I recognize this is noise? And B, how do I remove this noise? While making sure that the rest of the function is not affected. Right? Of course, you could apply some kind of a global smoothing operator, right? But these global smoothing operators would transform the function everywhere. They would even affect the maximum at 90. Whereas what I want is something like this in the middle, right? I would like to chop off this noise and without affecting the function anywhere else, right? The contour tree allows us to perform such simplification. How does it do that? So let's imagine that we just have the abstract representation of the contour tree, right? And every arc in this graph, right, can be assigned a particular weight, right? A weight for it, which is equal to the difference in function value. So for example, this arc has a weight 80 minus 50, which is 30, right? So this 30 is the cost associated with removing this arc, right? So now with these weights assigned, I could apply a very simple greedy algorithm to remove those arcs which have low weight. But what does this correspond to? If I begin with leaves, such as 80, right, and prune them, right? If I prune them by removing the node and the arc connected to 80, then essentially what I'm doing is I am knocking out one of the mountains, right? One of the mountains, which in the earlier terminology, it was a cylinder, right? It was a collection of level sets that started from 50 and went all the way up to 80, right? I have the mapping, remember, I have the mapping between the arc and the cylinder, so I can knock it off, right? But instead of thinking about the function and the domain, I can think in terms of just the tree and just knocking out leaves and arcs from the tree. This is much easier to think about it that way, right? Now, once I knock this off, I get essentially a node with degree 2. I can merge the arcs across this degree 2 node, and I end up having a single arc, 0 through 90. The 0 through 90 represents a single feature, a single mountain. What we have achieved in this process of leaf pruning and this vertex reduction, right, is a method for simplifying a function by removing its maxima, right, in pairs. I remove the maximum after pairing it with a saddle, right? So I go from this tree to a simpler tree. So the simplification process is essentially leaf pruning followed by vertex reduction, but it ends up helping us to remove noise in the data. There are different approaches to simplification, but all of them, at least in the context of topological structures, all of them follow this atomic operation of a critical point pair cancellation. So the 80-50 pair, critical point pair, was cancelled, right? That was cancelled to remove the mountain from the input, right? So in the interest of time, I won't talk about other measures, but if there is a question, I can answer. Okay. So there are different measures that can be used. So I'll skip this slide. There are other measures that can be used instead of the difference in function value to determine which arc to remove, right? So remember earlier we used the difference in function value, which is called height here. You could use, for example, something called something like the volume. The cylinder has a volume, right? You could use its volume to decide when to remove the, how to associate a weight with the arc. You could multiply the difference in function value with the volume to get hypervolume and use that to decide which arc to remove. Okay. Each measure has its own benefits, and these have been studied extensively in the visualization literature. Okay. This sequence of prune operations also allows us to re-represent the tree in a very natural way, right? This is called the branch tree decomposition. So let's look at an example to understand what this is. We have a domain here, looks like a cactus with the height function for simplicity. And the contour tree is shown on the right. You can see there are 3 minima here. There's one more minimum here that corresponds to this particular point, and multiple maxima. The branch tree decomposition is a representation of the tree which moves the focus away from nodes and arcs to trunk, branches, and their children branches, right? So the branch tree decomposition looks like this. There is a root branch C1, C14, and all branches that hang from that parent branch, and hierarchically so, right? How do you achieve this branching structure? So the way, there are many ways to do this. One approach is, it follows from the pruning strategy that we talked about. You start from the contour tree, you prune the smallest arc, right? So let's say in this case, it was C10, C8, you prune that arc, right? So now what you get is a simpler tree, right? You continue your pruning, right? You continue pruning until you are left with a single arc, right? That arc will correspond to the largest feature in your domain or in your function. And that single arc is the root branch, C1, C14, right? So in this case, if you can trace C1, C14 is here, right? So that is the root branch. The branch that you pruned, the penultimate branch that you pruned, can then be inserted, right? It's probably one of these, right? It's probably one of these. And then you recursively insert the other branches. So in a different example, this is probably clearer, right? So here on the left, you have the parent branch that you identified as DM, right? And there are other branches that stick out as children and other descendants from H, J, and so on, right? Why is it called a branch tree decomposition? Because you can think of this as a parent branch. The branch tree is a tree whose nodes are individual branches, right? So the root of this tree is the branch MD, right? So every branch is now a node in the branch tree. The children are child branches. So the two children of the parent branch MD are FB and GK, right? And so on. This branch tree decomposition is a very natural representation because every now node in this branch tree represents a feature, right? So essentially it's a dual representation. You go from nodes and arcs to branches and sub-branches. So this representation is often used in practice, and the pictures that I'm going to show in the applications are going to follow the branch tree decomposition, and hence I wanted to introduce that. Okay. So with that, I'm going to skip the discussion on algorithms because this will take us in a different direction. But I'm going to quickly say a little bit about the setup for sure. So far we haven't talked about input. How is the data available to us, right? So similar to how surfaces and shapes are available, functions are also available as samples. The domain is represented as a triangle mesh, for example, or a cube grid, a lattice. The function is specified at each vertex of this mesh or at discrete points. And we use interpolation, the simplest being linear interpolation. Right? If we have triangle elements, then just linear interpolation. So you end up getting a piecewise linear function. The ideas that we talked about, Morse theory and so on, have to be transported to the piecewise linear setting. There is, and this is possible. There's nice intuitive ways by which you could move those ideas to the piecewise linear setting, and then design algorithms. Right? Let me just talk about what is a key idea. Right? So remember, we talked about stability and the Morse lemma in order to classify critical points. Essentially, we want to look at the neighborhood of a point and be able to determine whether the function in the neighborhood is lower or greater than me, right? So let's take a very simple example in 1D. We have a vertex and we have a function associated with every vertex and linearly interpolated within the edge. How do I determine if this particular vertex is a minimum or a maximum? Right? One way to do that would be to look at the neighbors and check if both of them are higher or lower. Right? If both of them are higher, then you know that you are a minimum. If both of them are lower, you know that you are a maximum. Otherwise, you are a regular point. So this idea is extended by introducing the notion of neighborhood formally. This is what I'm going to skip. There are ways to extend the notion of neighborhood to lower and upper stars and so on. The idea of critical point classification is kind of very visual, so I'll introduce it using this picture. A minimum can be classified, for example, in 2D, by looking at all the neighbor vertices and the edges that lie between those vertices, right? So you look at those vertices. They are all shown in light black here, right? So this structure is called the link. All the vertices that are neighbors and the edges that connect them, right? So what I'm trying to trace here, that's called the link. I am interested in what is called the lower link, right? The subset of the link that lies below my function value. Right? So for a minimum, the lower link is empty, right? Because none of the neighbors have function value low, right? So the lower link is empty. The maximum can be identified by recognizing that the lower link is a circle, right? It has one connected component and one cycle. The lower link has one connected component and one cycle. The saddle has two connected components of the lower link. Right? So these are points with high function value. These are points with high function value. The lower link has two components. So again, topology comes to the rescue, right? So the topology of your lower link helps you distinguish between different types of critical points. This is how we identify critical points in practice. And this is a linear time algorithm. Of course, things in practice are not as easy as the theoretically as a theoretical situation where we handle smooth functions. What happens in practice is you can have so-called monkey saddles. This doesn't happen in for smooth functions. Smooth functions, you always have one direction in which the function goes up and one in which the function goes down for a saddle. But in practice, you can imagine that you can have not just two components of the lower link, but three, right, or four, and so on. These are handled by existing algorithms by just recognizing that monkey saddles can actually appear. There is a similar classification in 3D where the minimum is identified where the lower link is empty. The lower link is shown in blue, by the way. Right? The maximum is one where the lower link is a sphere with one component and one void, essentially. So it's just the sphere. The saddle, there are two types of saddles. There is the index 1 saddle has two connected components in its lower link, but no holes in the lower link. No holes in the lower link. Whereas the index 2 saddle has one connected component in its lower link. But this lower link is like an annulus. So it has one tunnel or one hole, right? So the lower link can be computed. It's essentially just a collection of triangles, vertices, and edges. And there are good algorithms to compute connected components. Just your simple graph connect, BFS, and so on works. There are nice algorithms that compute the number of holes in a mesh. So computing these two quantities allows you to classify the different types of critical points. Right? If you have more than two components, then depending on the number of components, you can recognize that you have a multi-saddle. Okay. Right. So there are certain assumptions that were made when we introduced Morse functions. We assumed no degeneracy and so on. Like I said, these assumptions are frequently broken, right, when you have data in practice. But there are good ways to handle these degeneracies. There are, but I'm not going to be able to talk about them. If you are interested, you can study something called the simulation of simplicity, which is a systematic way of perturbing your data so that all the degeneracies can be removed. Right? There is something called an equivalent of this called simulation of differentiability, which allows you to also take care of saddles. Okay. But here is the final property I want to talk about for contour trees before jumping into applications. So let's take this contour tree on the left. So note that I'm now showing the contour tree using the branch decomposition representation. There is a parent branch and there are children branches and so on. The blue nodes always represent minima, the red always represent maxima, and the green represents saddles in most of the pictures here. Right? So what did the contour tree represent? It represented change in number of connected components of the level set. Right? So the level sets are actually shown here for a 3D function. There is one component and then it switches to 3 or 4 components and so on. Right? Instead of looking at the level set, you can look at what lies below the level set. Right? So take the example of a terrain, right? The level set would be all circles, right? But I think I have an example that in here. So what you see in black here is the boundary of the black region is the level set. But let's look at what does the black region capture, right? Let's study the topology of the black region. This is everything below the level set, right? This is called the sub-level set, right? So its topology changes in simpler ways, right? It can only, two components can only merge because you're looking at everything below. You can only have merge events. There can be no split events, right? Because as you sweep up and you're looking everything below a particular function value, it's like dunking something into water, right? The component below the water level is what you're studying, right? So this is what we want to capture in the slides. I can move forward. So if I capture this change in topology of the lower, everything below a particular level set, then I get a tree, which is called the split tree or the joint tree, depending on what direction, whether you're going upwards or downwards, right? So if you go bottom to top, you get this notion of a split tree, right? So where you have only merge events as you go up. And if you come top to bottom, you again have only merge events as you come down. That's called the joint tree. So note that if you are only capturing merge events, think union events, right? This is easier to capture. It turns out that the joint tree plus the split tree is equal to the contour tree. And this was formally proved about 10 years, well, in a 2003 paper by Carr and others. And since then, this idea of splitting a contour tree into two simpler trees has been the central idea for designing fast algorithms to compute the contour tree. Right? And I wanted to introduce this because several data structures for storing arbitrary surfaces, right, which have different genus and so on, also use an idea like this, where they take the original representation and represent it as a collection of trees. This allows for fast changes to the representation, because you have trees, it's easier to modify them. Okay, so the join and split tree together form the contour tree. And there are many algorithms for computing the contour tree and the Reeb graph. I'm only giving you a sample here from a while ago. There are very fast algorithms available, parallel algorithms available, right? This is not something that I'll be able to cover today, right? But you can look up, there is 4 or 5 groups who focus on fast computation of the contour tree and the Reeb graph. And more recent times, there are even distributed algorithms that run even up to that scale up to 1,000 cores and so on, and have been deployed on the field. What I would like to, I think we already covered the contour tree and structure. So I want to jump to application so that you get some sense in the next 20 minutes or so on different applications of the topological structure that we have seen so far, right? I want to start with an application that first got popular in graphics, essentially symmetry, right? So symmetry is something we see in our day-to-day life. It appears in nature it's quite natural thing to have symmetry in, for example, you see it in biomolecules, in virus, for example. Often it is used to even solve for the structure of molecules. Some of the classic approaches that are used in biology and biophysics to solve for the structure of some molecules use inherent information about their symmetry. Symmetry appears in engineering applications often. Different kinds of flows are symmetric. They have different periodic boundary conditions and so on. In many cases, the absence of symmetry is also something that is of interest, because either this means that there is some kind of an outlier or there is a bug in your code, right? Recognize for identifying symmetry. And later we worked on computing symmetry in scalar fields. So recognizing this symmetry allows us to solve many interesting problems. One particular problem is symmetry-aware visualization.